Okay, next speaker, Paul Schenk, and he will present the origin on central pits and domes on Ceres, dome mapping constraints, and Ganymede comparison. Okay.
Forgot how it goes on. Okay, thanks. All right, we've heard a lot about the bright spot at Occator today, and I'm going to try and argue that you can't really understand that feature and how it formed without looking at the structure in which it formed, which is the topic of the talk today, and that is this central depression and also the central dome that occurs in the shadows there. This is a spectacular oblique image that Dawn acquired. And the mechanism for doing that is to compare it to central pits that you see on Ganymede and Callisto and other icy satellites. So just to set the scene here, this is a color-coded base map with color representing topography, and here's the rim is just outside the scene. This is the floor of the crater. This is the flat deposit, which is interpreted as a melt sheet, and then this is the central structure, which we're going to look at in just a second, which is depressed. About half a kilometer or more, almost 10 kilometers wide, and flanked by these large massifs to the west and maybe a smaller one to the east here, and then this small central dome right in the center, which is about 2 kilometers wide and about half a kilometer high. And this is the close-up of that. This is the three-color framing camera mosaic showing the structure, and the text here outlines the interpreted stratigraphy of the event, which is basically a large impact, of course, forming the crater in the central pit, and then because of residual heat, you get deposition of bright salts and carbonate-rich fluids, forming the bright deposit at some point thereafter, and then subsequent to that, the fracturing, which breaks up the surface of the salt deposit and fractures it and uplifts it through a variety of potential mechanisms, which we may have time to talk about later on. So you do see central pits on other bodies. They're very rare on the silicate planets, Mercury, Moon, and Mars, but they're ubiquitous on the large icy satellites Ganymede and Callisto at diameters larger than 25 kilometers across. And it turns out they're also ubiquitous on Ceres at diameters of 75 kilometers across, where you can actually resolve the central structure, where it's not been obliterated by their other features, subsequent features. They're in fact similar in morphology and relative dimensions, as this plot shows. They're about the same ratio of pit width to crater diameter on Ceres as they are on Ganymede. And this example shows this is a shaded relief version of the topography, so it wipes out the albedo stain, but you see this massif standing off to one side, and you see the same sort of thing here on the Callisto. There's a large massif to the east, but it's actually rimless around most of it, so that's fairly similar to what you see at Occator. So basically you have shallow depressions 1 to 2 kilometers deep, flanked by irregular massifs. Now, it turns out that this is actually, for in the case of Ceres, this is approximately the diameter you expect it. When you examine transition diameters on icy satellites, that is the transition from one morphology to the next more complex morphology, then to the next more complex morphology, in this case from central peaks to central pits, from simple craters. And if you plot those up, they form an inverse correlation with surface gravity. For the icy satellites that have been measured so far. And then when you plot Ceres, which is the points circled in red here, they lie exactly on the icy satellite line, so it indicates that there's a strong correlation there, that the surface of Ceres is dominated by the icy fraction of the crust, at least during the impact event, which is a very dynamic, high-stress environment. And that includes central pits here as well, the largest morphologies that you see on any of these bodies. There is one exception to this rule, however, and that is the Saturnian and Uranian and, as it turns out, the Plutonian moon as well. When you look at those craters on the plot, you don't see any of the Saturnian satellites plotted here. That's because there is no transition to the central pit. You just don't see them. Even in craters larger than 300 to 400 kilometers across, there's actually only one on Tethys, that's Odysseus, that has a central pit morphology, and that's like 425 kilometers. It's off scale here. So instead, you see just central peaks all the way through to the largest diameters. So something's very different on Ceres, and this is despite the fact that the surface gravity is very similar. The only difference is that the icy satellites are presumably more ice-rich, they should be easier to melt, and yet we don't see these sorts of things. The only other difference is that the outer icy satellites, because they're so much further from the sun, are colder. They're considerably colder. Their surface temperatures are more like 100 degrees or less. So there's an indication there that temperature is a potential control on pit morphologies. And we may see something of that effect on Ceres as well. And I apologize for this poor version of the topography. But the large crater near the South Pole, that's about 70 degrees south, I believe, Zadini, has actually a classic central peak. It should have a pit because it's well within the expression of Ceres at that diameter, which all have central pits. But instead, it has a central peak. Now, it's one example. It's not the numbers of large craters at the pole are not very many, so we don't have very many samples, but it's an indication that we may possibly be seeing a similar effect on Ceres itself because the poles are considerably colder than the equator. So another indication that temperature may be controlling things. And as an aside, you can ask, well, if Occator had formed at the pole, what would the central structure look like? Well, these are measurements of peak width and peak height on other craters on Ceres, and the Occator point would plot about here, so you can measure that, and it would be about 30 kilometers across and about 2 kilometers high, which actually fits very well with the observed massifs we see at Occator, except that the top of the cone is missing. It's been blown away or erased or whatever the mechanism is. So it sort of makes sense that it tried to form a peak, but it failed. The question is why? So we have the central dome as well, and I'm going to talk just briefly about this, but the focus is on the pits, of course. We have domes in central pit craters on Ganymede and Callisto. This is a classic example of the crater on large crater on Callisto. The dome is considerably larger. It's about factor of 10 larger than the dome on Ceres. And you can see that's cracked by a fine scale network of small fractures. And we see lots of these smaller domes, lots of these domes in smaller craters on Ganymede and Callisto. The arrows point to the domes, but we never got high-resolution images on these, so we don't know whether they're fractured, but we assume that when we get there again to Ganymede that these domes will be fractured in the same way as Occator is, but we're just going to have to wait to find that out. Now, this suggests that the stratigraphy suggests that the cracking of the dome at Occator occurred after the bright material is in place because it appears to fracture it. And I've heard the term referencing the dome as being cryovolcanic, and I would hesitate to use that word. I think that's a word laced with too much baggage. I would tend to try to find a different word to describe that. We don't really know why that dome occurred. It could be freeze expansion of water-rich material beneath, which would not be volcanic per se, but it also could be laccolithic inflation, lifting the surface up. There's different ways of doing it. The dome, looking at the shape of the dome, this is the height plotted against the diameter of the dome on Occator, plotted against the very few domes that we have measurements on Ganymede and Callisto. We've only got about 5 of them. That's again because we don't have the data yet. And it's actually, there does seem to be a trend on Ganymede and Callisto that indicates a modest increase in the dome height with size, but Occator doesn't fit on that curve. I don't know why. It's only one example. We don't know whether the Ceres line would go like this or go parallel to this. Again, it's just one point. We don't have enough information to say, but it could be that there's maybe a limiting height to the dome that they always come up to be about half a kilometer high or higher. So it's really just hard to say where this trend would actually go without returning to Ganymede and finding another dome on Ceres, which we're not going to do because we already know that. Okay, so we have a couple of constraints. We know that a central pit formation is diagnostic on the icy bodies, on the icy satellites, and also on Ceres, which indicates that it's a fundamental process. We have to explain it in order to explain the to explain the bright spot. We have to figure out what's going on in order to figure out how the bright material got to the surface. So that's an important part. Temperature may be a control on pit formation. Now, I'm going to go through the proposed mechanisms. There's at least 5 proposed mechanisms for central pits on icy satellites. And if anybody tells you they know how central pits form, they're liars. It's fake theory. It's sad. It's just, but we'll go through them anyway, just for the fun of it. Because there are some of the models that we can eliminate, I think, fairly safely. One is the idea that basically the surface underneath the central complex was vapor-rich, it was volatile-rich, and it basically exploded when the pressure was released. And this might work on Mars. There's some evidence that might work on Mars, but you don't see any evidence of explosive debris surrounding the pit. There's no evidence that an explosion actually occurred at that time. So I think this one can be fairly safely put in the dustbin. The next one is essentially the collapse of a weak central peak. It was not strong enough to support the height and the weight of the mountain that was formed, and it basically collapsed. Now, there are variations on this theme where there's basically some sort of vertical oscillation that occurred. But basically, this idea is also kind of difficult to reconcile with the observation because there's no pile of debris, if you will, in the floor of the pit. It should be choked with its own debris if it collapsed. It should be just a rubble pile, and we don't see that. So I think we can fairly safely eliminate this one, at least for Ceres. Another idea, and pardon the simple graphics, I did this at 3 a.m. last night, so it's the best I could do. But the other idea is one that basically, for the icy satellites at least, you may have impacted into a layered target, one that had a brittle layer over a ductile layer, and then the ductile layer sort of kind of overshot during the rebound and sort of poked its way up through the crust and then settled back down again, pushing the material out to the side. And that might work for icy satellites. It's hard to really say because, again, we didn't get the high-resolution observations we needed from Galileo, so this model was never really properly tested. But it's not really consistent with the idea that the dome occurred after the impact event on Ceres. So I don't think it really works for us here. The next idea is that you have basically, during the impact event, the temperature is high enough in the central structure that you have sort of like a conical plug of liquid material that formed during the impact event. And then when the rebound occurred, that material sort of moved out. And this was proposed again for icy satellites where you're dealing with a lot of water. The model is somewhat controversial because in an axisymmetric system, there are ambiguities that formed right at the center of the model. So it's not entirely clear that this interpretation is physically realistic. There are volume problems. There's a lot of material to get rid of. I mean, the idea is that the water drained into the basement, the fractured basement. So it's really hard to say that really worked. You don't see a lot of mixed debris. Yeah, maybe, but hard to really to say. There's a possible Syrian variation on this, and that comes from the observation that pit formation might correlate to some degree with the formation of impact melt deposits on Ceres. Here's 2 more examples of central pit craters. Gaue has a central pit. It doesn't even have a rim around it. It's just basically a shallow depression. And it's surrounded by a lot of smooth impact melt sort of things. And then Tohuru, which is further to the south, actually has a lot of its central peak still remaining, but there's a big hole in it. It's basically like Mount St. Helens. Part of it just got removed. And there's a bit of impact melt down here. So there's some indication that they might correlate. So we're going to relook at that previous model in a slightly different cast. and consider the collapse of the central peak consisting more of impact mud, which is a mixed water and rock material. And I would probably redraw this to be flat-floored during the early stages of the impact prior to rebound. But basically it gives you the idea that there, because of the high temperatures at the center, you get this sort of mixed medium. And then when the floor uplifts and it tries to make the central peak, then it displaces all that material and you get a big slosh of material outward. And then the dome would form after that when you have various other processes like refreezing and sort of stuff like that. So considering all the information, all the constraints we have, and the fact that we really need to go back and do some more modeling, this one seems to be the best explanation for what I think is going on. So final slide is that the pit and the dome are key parts of the Occator Ceres facula puzzle. If we're going to explain the bright deposit there, we have to understand what's going on in the center, how this structure formed, because it's the gateway for the material to get to the surface. The central pit observations that we have on the icy satellites and for Ceres all seem to suggest that there's a temperature dependence involved here that may control what's going on. We can probably eliminate the mechanical collapse of the central peak, and the explosive origin is probably unlikely to explain what's going on any of the bodies, actually. So we're sort of leaning towards the idea that maybe concentration of impact melt in the central peak area during the formation process, and then displacement of that during the uplift of the central area, giant sloshing of impact melt all over the place, is probably a fair guess as to what's going on. It's probably very simplistic, however. There's probably more things going on. The fact that it does not happen, this process does not happen on the Saturnian or the Uranian moons or on Charon, Pluto's large moon, is probably because you don't get any impact melt forming at all. The temperatures are too low, and the impact event doesn't bring it up high enough to give you a significant amount of impact melt. The dome and Ceres facula form after the emplacement, and I see I'm run out of time, so I'll call it there.
Thank you, Paul. Any questions? Yeah?
Paul, you say that the formation of the pits is temperature dependent. Do you mean the surface temperature, or do you mean the impact temperature?
Both, because you have to start with a certain condition. And if the surface is very cold, it has to use a lot more energy to heat that surface. If it's near the melting point anyway, which is Ceres is kind of close to it, then it's got to use less energy and can melt it easier.
Might also depend on the size of
Oh yes, of course. And that's why you don't get this until you get to the larger diameters. The smaller craters, you're just not going to get enough heat to melt anything. So you have to get to a much larger structure, like in Ceres, it's 75 kilometers or larger, roughly speaking. You don't get pits in craters anything smaller than that. So yeah, that's exactly right.
How much ice do you need before a planet starts pretending that it's an icy satellite as opposed to a terrestrial inner planet?
Yeah, that's a good question. As Carol mentioned way back at the beginning of this afternoon, the geophysical models seem to indicate that maybe 30% or less of the crust is composed of water ice. And indeed, when you look at the viscous relaxation of craters on Ceres, you don't see it, hardly at all. You see a little bit, but you don't see the magnitude, which indicates the crust is pretty stiff. But all these transitions indicate that it's ice that's dominating. And when I talk to people like Gareth Collins, who actually do numerical models, they're telling me that 30% is actually not a bad estimate. You can actually put 30% ice in a crust like this, and under impact conditions, because of the high stress, it'll actually behave according to the physics of the ice rather than the rock.
Okay, any more questions?
taking advantage
Paul.
of the law of missing talk here, yes.
So everything makes sense, except that at the end of your model where you stop talking, you still have a pit, and you need to get a dome. So, and getting that material up is where you might want to debate what the definition of cryovolcanism is, but certainly something is filling the void, and it's getting there from...
It's trying to. It
Well,
doesn't quite do it.
Okay.
Yes, I thought about that as I was reviewing my slides earlier. It's like, yeah, this sort of works, but you still ended up with a pit. Why doesn't that material fill the pit back in? Why do you always end up with this depression? And I just don't understand that mechanism right now. Maybe it's just the way the material, the impact melt moves off, and it sort of solidifies too fast to go back in. I don't know, or else something maybe draining it down again or something. There's a key piece of this puzzle that we're missing, and we need to think about it some more. So yeah, basically, yeah.